be recorded as well. This week has been a roller coaster week between recovering from dental surgery last week and then 3 weeks before, 2 weeks, well, yeah, 2 weeks before that. And we should be live on YouTube now. If someone can just put in the chat or whatever that we are live, that would be really helpful.
Yeah, it says meeting is now streaming live on YouTube.
Okay, good. Okay, awesome. Thanks, Lou. I appreciate it. And yeah, I see it coming up. So I'm going to pause this here. Yep, I see it. Okay. I don't want it playing at the same time as all. I have no. It's been a roller coaster week between recovering. There we go. You heard it playing. So I put it on pause there. So that way, and I'm going to leave it like that. And hopefully it won't eat up what bandwidth I got left. All right. Well, welcome to our 7th annual TECHCON and a new adventure. And I'm trying to remember to look at the camera here for the benefit of those there on YouTube and on Zoom this morning. I'm using an old smartphone because the camera quality is just so much better than the one built into this laptop, which looked real grainy looking. I wasn't happy with it. So, and when there's some ground rules here, we will mute everyone except our presenter when they start their presentation. Then we will unmute everybody, and then you may ask questions. So if a dog barks in the background, your wife calls you or whatever, it won't lock up the presentation and knock our speakers off. So we're trying to do that the best we can. You could make comments via the chat section. Don't forget about your chat. You can ask questions there or post questions. We'll take them. And if someone could go over to YouTube and volunteer to look for comments there, when we get to Q&A, we can try to get some off of YouTube as well for those that, at the moment, we're up to 17 participants, so we're not anywhere near the 100 yet. So that won't be and I'm sure more will be trickling in throughout the morning. And I have the waiting room engaged so we don't get to over 100 and then our speakers can't get in, which is the worst thing that could happen. So again, pray for me and think about me as I go through this. This is all new ground. And at this time, I'm going to turn it over to our section manager so he can make his comments this morning. Mike, and we'll say good morning to you. And I'm looking here between the camera and the screen. And you go ahead and unmute yourself and give us your comments, whatever you like to share.
What do you want to hear?
Anything you want to say, Mike. It don't matter. Humor.
Well, I want to say I'm glad to be part of this group as the new section manager for the West Central Florida section. I assume there'll be some women involved later. So ladies and gentlemen, welcome aboard to the 7th annual TECHCON. And it's going to be interesting this year. I know with the social distancing, and boy, are we social distancing. It's going to be an interesting concept this year. Hopefully next year we'll be able to get back and do it in person. I see Randy out there. I see Mr. Lunsford there, who I appointed as our section public information coordinator. So he took over from Rich N4ESS, who had asked me to find somebody. So I did that, and that's where we're at. I don't, as far as the section goes, I don't intend to make a heck of a lot of changes. It works well as it is, and I'm going to leave it at that. I'm not going to blow anything up, hopefully, and have Daryl mad at me later on down the road. But I'll do my best. Oh, I forgot Randy over there. I see you over there, my friend. Missed you. But I will be in the background here. And for those of you, and the faces I'm seeing, I'm sure you all do, remember Mr. Wizard. Well, our Mr. Wizard is Daryl Davis, KT4WX, and I'm going to turn the show over to him.
Oh, thank you, Mike. And yeah, I don't know about Wizard, maybe has been or leftover or whatever. I'll be glad I get Starlink here in a few months, and then internet access hopefully won't be a problem. Well, it is 0900 hours, so the little presentation I planned. What's that, Mike?
I signed up for it too, so there you go.
Hey, there you go. Yeah, we're both looking forward to it. Out here in the country, we don't have any other choices for internet service. So without further ado, let's go. So we'll stay on time here. I'm going to go ahead and turn it over to Gordon here. So I'm going to mute everybody at this time. And let me see, be sure that, okay, I have done this rightly. Mute all, and I'm going to unmute Gordon here so he can go ahead and take it away here. And so that way he can go uninterrupted. If I can get asked, what's this here? Okay, I see him bringing his desktop up. And okay, Gordon, I'm working on getting you unmuted here. And then while Gordon is getting his, let me see there. Asked to unmute. Let's see. And
Can you guys hear me okay now?
Yeah, you're unmuted. You're good to go.
Okay, good.
Go ahead.
I got two computers. I'm not sure which one's going to do better, but we'll do the best we can. So there have been difficulties in the past with my internet speed here. So if something isn't working, if you could tell me. I don't think I can read the chat at the same time I'm doing it. So if something shows up in the chat, if someone could speak up, then I will know that there's something I need to pay attention to. This talk is about building a ham radio ventilator, which consumed the beginning of last year. But I'm going to start with a shameless plug for their March 19th exercise. We're doing the Whirlwind Boom exercise. It's a large-scale exercise. It's available to anybody. Florida, Southeast, doesn't really matter. It's designed to increase interoperability, which doesn't just mean frequencies. It means experience working with each other. So we have people from ARES groups. We have individual resource units. That means volunteer hams. We have Florida Baptist Disaster Agency, which is an NGO-served agency. We have the Florida Division of Emergency Management, which is a government agency. We have multiple EOCs, and we have the SHARES, which is a federal DHS backup communications effort. This exercise is it's very short. It's only from 7 to 9 p.m. on Friday evening, March 19th. That time was dictated by the availability of the communications trailer at the Florida Baptist Disaster Relief, so we had to go with what we had. This operation involves a massive tornado volley that crossed the state of Florida. We're using imaginary names so we don't get ourselves in trouble with impersonation claims. However, it was made worse by a terrorist bombing in Johnsonville in the northeast corner, which damages the internet. We have online incident action plan and an HSEP exercise plan. So we're trying to do this as professionally as possible. If you want to go to our webpage, you can, how do I do this? You can see all of this kind of stuff in a calendar that we keep, that we have right now. And here's the Friday, March 19th exercise, and there are all the links. So you can register for the exercise. You can read all the information about the exercise. You can read to your heart's content. Right after I finish this talk, I'm joining a Zoom call with volunteer net controls for this exercise. You would not believe how ham radio can get completely ignored during a massive catastrophe. And I'll be giving them a short talk about what happened during the derecho in August just last year in Iowa, and how nobody took advantage of ham radio or shares to move crucial information. And as a result, the state of Iowa screwed up and turned away resources. You would not believe how it screwed up. If you are not involved, if you are not connected, you are not going to be called on in a disaster. So it's crucial that volunteers begin to get involved. I think I covered everything there. Yes, I did. This talk is a dual theme talk. We're going to talk about the technical development of the ham radio ventilator. We're going to talk about project management as well, because this was a huge problem for us to try to create a ventilator in such a short period of time. And we screwed up several things, and you'll get to hear all about that. Okay, so why does this benefit the amateur service, or what does this have to do with the amateur service? As defined by the FCC, One of the goals of the amateur service is to expand the existing reservoir of trained operators, technicians, and electronics experts. We're supposed to have a group of people who know something about electronics and benefit the world when the chips are down. And this ventilator was an example of that. So what was the situation? I got to move this thing so I can see my own slides. We were supposed to have a huge mortality, and we were all going to die by April 19th. That's what we were being told. The reports back then were that there was no human immunity, that there was a 3 to 4% mortality. That was completely incorrect. There was an exponential growth expected. Well, we did see that from time to time. It was supposed to overwhelm hospitals. Bodies were stacking up. This actually did happen in some portions of the world, and literally the doctors where I had just retired from were being told that we were going to be completely overwhelmed and that we were going to completely run out of resources. We were told that we needed ventilators now. This was March, February last year. The FDA was opening up the emergency usage authorization. The same thing that was done for the vaccines was being done for the ventilators. They had a quote, simple list of requirements. It was only 28 pages long, and it only referenced thousands of other pages of requirements. So a good friend of mine, Dr. Sim Lampetang, and an engineer, asked me for help. And at first I blew him off. Then I realized he was actually going to succeed, and so I better get involved and help, or I was going to be left out. So my pride got me going. Let me tell you a little bit about normal human ventilation, since you guys are amateur radio operators. Some of you are probably involved in this stuff. Normal breath is approximately 500 cc's, so it's about a quarter of a 2-liter bottle of Coke. Normal lungs are very compliant, so they only use 25 to 35 centimeters of water pressure. For comparison, 33 feet of water is air pressure, so this is very low pressure. This is 0.4 pounds per square inch. It has to be very accurately delivered. The respiratory rate has to be in the range of 10 to 30 in order to have optimal transfer of power. You can think of that as SWR matching. And we want to maintain an end expiratory pressure at a level chosen between 5 and 20 centimeters of water, and that's designed to keep boggy lungs open. The United States was said to be tens and thousands of ventilators short. We only had a strategic cache of 10,000 ventilators. And there was this dude named Cuomo, who none of us knew much about at that point, but he was loudly demanding 40,000 ventilators and ships and hospitals in his state. The ventilator mortality, friends of mine were calling me up and telling me, Gordon, we put them on the vent and they die. It was 80% at that point. So going on a ventilator was very close to a death sentence. They wanted us to create a way to allow patients to breathe on their own if possible, even though the FDA, EUA did not require this. As you can tell, there was a lot of confusion. Ventilators are expensive devices. We're talking $50,000 to $100,000. We had supply constraints. Normal ventilator parts were disappearing. Everybody and his brother, General Motors and everybody else were buying up ventilator parts to construct ventilators at the request of the government. So we were trying to use unconventional parts. Ventilator valves were in very short supply, so we were going to use sprinkler valves from your lawn sprinkler. We were going to drive it with compressed air, which is a similar pressure to the pressure that drives normal ICU ventilators, by the way. So when the University of Florida came to me, they had an airway system. It was a beginning airway system, but they had no way to turn it on and off. And in just about 24 hours, I turned this around and created my famous Sunday morning kitchen table demo. And that is the demo. I'm hoping you guys can hear the sound. I tried to set it up so you could. There's a test lung there in the background, and ventilator airway assembly is the white stuff. There are ventilator hoses. There's an Arduino Uno, and I had some 2N3055 transistors acting as the driver, and that was turning the valves on and off from the compressed air supply. My bright idea for their ventilator was to control it with an Arduino. And I knew just a little bit about an Arduino because I had been fiddling with the micro BitX radios that Ashhar had created. See, there's something showing 2. Are there any questions, or is there a chat that I need to deal with? Okay, hearing nothing. So enter ham radio volunteer project management. I needed brain power. I didn't know enough to make this happen in the required time frame. I needed help. So I turned to people who are known to be experts by their proven contributions to amateur radio. We needed people who knew how to design, prototype, build, and manufacture equipment, and we had to do it in a space of a few weeks. So I turned to Jack Purdom, W-A-T-E-E, who is a world famous programming author. I turned to Ashhar Farhan, BU2ESE. This man is independently wealthy, I've come to understand. He's an entrepreneur. He's a creator of BitX. He's also a voice over IP telephone pioneer who owns a telephone company. And he's a creator of a satellite contract company to put satellites into orbit for his nation of India. So what is an IDE? It's an integrated development environment, and that's what you use to program an Arduino. It runs on your personal computer, allows you to develop and compile working source code. It uploads it to a $3 Arduino from China, and it's free. And that's one of the better parts for me. Let's see if I can move this over now. This thing is sort of in my way. Good, I got it out of my way. Okay, for you, I want you to know basically how you load this IDE. This is duck soup simple. It's a free system to load the software. You go to their page, you download the IDE, and you install the thing, and then it allows you to load what's called a sketch. That's the source code. You hit a button, you hit another button, and then bingo, the software begins to run on your Arduino. There can be some glitches in the way, but it's generally very simple. It's available for both the Windows and the Macintosh system. There's also a web editor, but I don't recommend that. It's extremely slow. I mean, glacially slow. The Windows installer is what I used. They try to take money from you, but I just hit the button that says download, install it on your computer, answer a prompt yes where you want it to be installed. I recommend that you install it wherever it wants to install it. It comes preloaded with examples. So you can just click on the examples and they have basics, digital, analog communications, whatever. The most basic one is Blink. Blink turns on and off an LED that comes built in on the Arduino. And you can actually examine that code and it will give you an idea how this works. You could start with that code and you know, kids in elementary school are doing this these days. So it's really, if you're willing to just sit down after breakfast and fiddle with it for a minute, you can figure this out. You connect a little USB cable over to the Arduino. There are all kinds of educational kits. You can actually do ordinary programming as well. The cool thing about the Arduino is it includes many A to D converters, so it can measure voltages. Although it does not have a D to A converter, it does include digital outputs that are pulse width modulated. And I've seen now that there is a transceiver folks are building that actually receives and transmits single sideband on the ham radio bands using an Arduino for digital modulation and demodulation. It's amazing what you can do with this device. So I went to the established group for BitX development, which from its earlier days was known as BitX20 at groups.io, and asked for help. And I immediately overwhelmed their forum. I just took over their forum. Jack Purdom, who knows how to deal with these kinds of issues, immediately created a new forum for us, which was known as Ventilator Developers at groups.io. We had 200 contributors show up, or lurkers, you can't tell them apart, and there were hundreds and hundreds, maybe thousands of posts. We were passing code back and forth every single day. Engineering discussions were being held in all different nooks and crannies of that thing, thread after thread after thread. So we had brain power. We had people writing code, we had code being tested. Now we needed hardware. Okay. More than 2,000 posts. It was like Google for developing a ventilator. If you had a question, you could either ask them or you could ask Google. And you were likely to get a scholarly reply in minutes to hours from this assembled group of experts from all over the world. Okay, so how do we make the air go into the patient? So our plan was to open the inspiratory sprinkler valve and air will flow out into the open end. But you've got to stop it from just escaping to the rest of the world. So you have to have a valve somewhere that closes. You want air to go into the patient instead of just out into the world. So Sim had solved that by building a fancy but elegant valve with a bicycle inner tube. It was positioned so that a portion of it was exposed to the inspiratory limb, the limb that's supposed to go to the patient. That would see the air pressure and blow up, and it would obstruct the expiratory limb through a crossover portion. And that way air would go into the patient. When you close the sprinkler valve, this bicycle thing would automatically just deflate, and it would let the air come back out of the patient. Normally a ventilator system has 2 valves in it, but Sim had managed to do it with sprinkler valve and this bicycle valve. The problem was the inner tubes would rip after a few thousand cycles, and then this ventilator would be kaput. We needed 1 million cycles. Day by day, we managed to improve it to over 300,000 proven cycles. We had one ham radio volunteer who did hundreds of thousands of cycles. It was astonishing the amount of work that these guys do. I can't list all the people who did experiments, hardware experiments, software experiments. I wrote multiple press releases for these folks, and I tried to give them credit. Mark L. Winsenreed, who was evidently famous, WA9ZCO, he figured out how to switch the spring in an orbit, it's a commercial sprinkler valve, and turn it from normally closed to normally open and have it have incredibly low resistance when open. This was an enormous advantage. He had figured out how to make an expiratory valve for the ventilator circuit. So I tried to explain this to the University of Florida team, which was meeting every morning at about 9 o'clock via Zoom or something similar to it. They just ignored me because they were so overwhelmed. They didn't understand what Mark had done. So out of frustration, a couple days later, I built what Mark had done, and I then demonstrated it to the team over Zoom. Remember, we're all terrified. We're all sitting in our little houses, can't even go to campus. And I demonstrated them how this was very superior to what they were doing. And this is an example of another ham radio operator coming to the rescue. We needed ham testers. We had multiple testers doing our tests all over the nation. Bob Benedict, 88CGH, he went over 2 million cycles on some of our ventilator designs. Just a huge number of tests. Ashhar Farhan was busy at that point developing a control board. I can't read my whole screen, but he was taking input from all kinds of people. So Ashhar designed our 0.1 board. We had a design and we needed to know if it worked, but you couldn't do anything. The whole nation. He was having to secretly move from building to building to avoid being arrested. Luckily, another guy stood up, a gentleman from the OBGYN department at the University of Florida, knew how to hand create a printed circuit board. And he created a homemade printed circuit board for us in a matter of a few days. I'd never seen this done before. He had real trouble because the traces were so small. You evidently have to solder lead onto these traces and fix busted traces with small pieces of wire. He built us our very first board, and I was able to test that board and prove that it actually worked. So we now knew we had a design that potentially could work, but we had been moving so fast that we already had a new design. So Ashhar then came out with a new design, and he succeeded in his 0.1 design, so we decided to go with his 1.0 design. Ashhar builds on KiCad. I don't know how to use KiCad. I only knew how to use dip trace. So I had to sit down and learn how KiCad worked in order to figure out whether or not I thought his design, because I was having to make decisions every day. Is this worth going with? We were having to move forward towards manufacturing. It was the same project, the same process that the vaccine developers were using. We're all volunteers. We don't know what the heck we're doing. So I was just being force-fed knowledge constantly by this group. So then Dr. Stapleton here, a ham radio operator in Gainesville, Florida, another person of the University of Florida, designed his own board and managed to get them put together, fabricated, delivered. He solders them together and he proceeds to deliver board after board to my front porch. So now the University of Florida team is being overwhelmed with boards. We spent almost $2,000 getting boards rush made for the, quote, impending immediate crisis. Meanwhile, they're busy doing a GoFundMe effort on the UF webpage to get the money to do all this stuff. And so now we have two parallel designs going. At that point on a Friday, Sim called me up and said, we need to have a battery. Where's the battery? Battery? I didn't know there was supposed to be a battery. So overnight, I designed a transducer and battery backup board, and I had it up and running within a week. This was kind of an amazing thing. It's a very stupid board, but I had to design anything that I could get built. We made a mistake. We were measuring pressures with a really slick device that's made by Bosch, the BMP 180 or 280. It's used in those little vaping cigarettes. It's dirt cheap. It's used in automotive systems, and it's extremely accurate at measuring pressures. But we had problems. We're supply chain limited. Ashhar only has a 180. I can only get 280s, a newer version. The software is different for the two, and I failed to realize how tiny this thing is. In that picture, those wires are not normal wires. Those are single strands from an Ethernet cable. I think they're 26 gauge. I don't really know what they are. We failed to order the measurement chip on a leaded carrier. Instead, I was stuck with trying to solder to that thing. That's a normal perf board in the background to hold the wires, normal size perf board, 1/10 of an inch centers, and I'm soldering to that thing under a magnifying glass. It took an hour to solder one of them together. But this is how do we connect this thing? The one that we have on a leaded carrier is a non-differential transducer, but we need to connect it up to an airway. And it has nothing that you can connect a tube to. So we glued these little parts from automotive vacuum tubing to them, and we learned how to do it. You use one dab of glue just to get it mechanically centered, and then you use a dab of glue around it on the second go around, because if you obstruct the pinhole opening into the BMP 280, you've ruined your pressure monitor. So the physical construction just took us a lot to learn how to do. Then we ran into problem with libraries. In order to use these devices to measure the pressures, we had to add some libraries. There were different libraries for the 180 that was the only one that Ashhar had in India, and the 280, which was the only one that I had in the United States. And these libraries had issues that we didn't understand. We were very concerned that this system could be crashed. Of course, if it crashed, then the patient might die. So this is an issue, and we had to learn how to load these libraries and library manager, and it's just no end to the problem. In order to connect up to an individual Arduino, you had to pick the board type, the port, which meant you had to learn how to use Device Manager on Windows. You had to compile, you had to upload, and you had to learn how to use the serial monitor to watch what was going on. Menus. This thing had to be operated by nurses. Now, I don't know if you know, they're the two dumbest people in the world are doctors and nurses, okay? If you give them something, I guarantee you they can find a way to break it or kill the patient. Trust me, I've been a doctor for 30 years, so I'm familiar with this. So Ashhar Farhan wrote the first code for the vent, and I worked on that code for weeks because the date that we were all going to die kept getting pushed back by these supposed national experts. First, we were going to die April 19th, then we're all going to die, well, it's a little later in April. Ashhar then rewrote the entire menu in a 3-day weekend. He would just disappear, and I couldn't find Ashhar, and I didn't know how to reach him. And he showed back up all of a sudden with a complete new menu system that actually was expandable and would allow us to add new features to this thing, which had been impossible before. In the meantime, I learned that Ashhar knew all kinds of things that I had no idea what to do. I was terrified of trying to call Ashhar by internet. I didn't know how to reach him. Turns out the dude runs a telephone company. So in the middle of the night, because we're 12 hours apart, my phone rings and it's Ashhar saying, here, this is how you call me for free. It's just amazing. Okay, so we ran into big problems with the I2C bus. There was a big concern that this could block if a reed failed, and everybody was concerned that this could happen. And if it happened, then the ventilator would come to a screeching halt because it was a stop for the entire code. So I wrote a testing routine where we would literally pull wires and see if the ventilator would die. Ashhar came up with a solution for this with a watchdog timer routine where we generated giveaway numbers. And if those numbers disappeared, then we knew the machine had died and had been rebooted by the watchdog timer. And then we would know that the I2C bus had failed, and we would ignore it thenceforth, and we would move forward with hard-coded numbers. Sort of like if your computer in your car dies, it goes to hard-coded numbers for how to set things. We also wrote a routine to reset the I2C bus. I never, ever saw a single failure of this that I didn't cause myself. I even tried to kill the I2C bus. I built a 6-foot length of I2C bus wire, and somebody's texting me. Okay, I don't need that, so I'm going to skip that. I carried it upstairs to my WinLink station, and I put it right next to it, and I ran 50 watts of HF, and I could not kill my 6-foot I2C bus. Then I held a Baofeng transceiver right next to it, and I tried to kill it with VHF or UHF, and I could not kill the I2C bus, but still, we were very concerned about this. Eventually, we found replacement libraries that significantly reduced the I2C failure issues. These were tricky libraries. So the mistake we made was we should have just gone to the developer of the library and said, fix this. And we could have saved all this effort if we just made phone calls. Okay, so now we came up, because of this new design that Al Winsenreid had come up with, we now had an active expiratory valve, and we could control both inspiration and expiration separately. And maybe we made a mistake by doing this in retrospect. We thought we were doing what the FDA wanted. When we tried to control the expiratory valve, we learned that the system would ring. Oh gosh, it was just huge ringing. The air would move back and forth, and our pressure sensor would read this pressure and then that pressure. They would open and close the valve and drive us nuts. On the right of this screen, I give you a plot of what the inspiratory pressure actually looked like in the ringing system. We basically had a nonlinear system, and it could oscillate like the devil. So we then went to PID controllers, and then we went to nonlinear adaptive hunting algorithms, and finally found a way to control this thing so that we could actually control the peak pressure. And we were building what basically was ending up as a near ICU level ventilator that could be manufactured in a third world garage. But we had made a mistake in our negotiations with the FDA. One of our team members had promised the FDA that we would actually have a manufacturer, not just a prototype design. There were all kinds of legal issues with this. We were terrified of being sued all over the world by this thing. This was totally unnecessary. We did not need to have a manufacturer. So huge effort then went into trying to find manufacturers who would actually build this thing and take the legal liability for us. This is me. That's one of my covers, and I have a full-size drawing laid out of where everything will fit and where the holes needed to be drilled in my attempts to create artwork for our manufacturer. We were able to prototype these ventilators. Normal researchers can't do that. The ham radio types who were brought up with vacuum tubes, we know how to solder. So we could build things, we could connect up tubing, we could actually build prototypes, and this was a huge advantage to the team. I want to point out again, ham radio is a significant source of experts to the nation. This is the PVC airway portion that was being worked on by other teams. There are all kinds of baffles and things in this, and low-pass filters to allow, I got to see what's on the bottom of this screen. I can't read it because of this stuff. PVC. The FDA was terrified of PVC. They were scared that it was going to give off vapors. It would kill the patient. This was crazy stuff. We had somebody at UF that actually knew how to measure the vapors given off by PVC. They actually demonstrated to the FDA that there was almost no vapors being given off by PVC that we got from Home Depot that had been sitting in their yard for a few weeks or months. And the FDA said, fine. They only wanted something to cover their rear end. This was all driven by lawyers. It's really crazy. Okay, so if you model this thing as a hamper, I got to move this out of my way. I have something in my way, and I got to find out how to move it. It's this great. Well, can't move it, so I'll give up. So basically, the inspiratory valve looks like a Class D switching amplifier to a ham radio. Then we have a transmission line that couples the energy, the air, over. And then there's a filter there that's a low-pass filter in ham radio speak. And there's an output monitoring system, which is basically like a current monitor for us. And because of this thing in my way, I can't see it. Now I don't know how to move it. Oh, I found out how to move it. So now I can see. We have a valve down here that's delivering power to control the amplifier, and that's our exciter. So this is sort of like our grid or base driving signal. So this thing can be looked at as a transmitter. And we were trying to explain the ringing, and we actually figured out ways to explain the ringing. So these two plenums here made out of PVC parts, those are low-pass filters designed to decrease the ringing by changing where the nodes of the system are. We've got all this tubing, and to keep track of the tubing, I've colored twine around it. You can see a differential pressure transducer over there. Here's our backup battery. So I'm having to build these things. Okay, so remember I told you that we spent all this money having these boards built? Well, the first set of boards arrived. These were actually constructed for us, and they wouldn't work. Kept overheating. They were $800 worth of boards, and they would just burn up. And it turned out we had some errors in the construction that caused the display to use way too much current, which would burn up the voltage regulator. And we had to add some resistors to drop the current that the LCD display was using and fix that problem. So we're into manufacturing alterations now. Okay, well, I thought we were doing great. And then all of a sudden, a ham in California proved to me that in one day, the background pressure in the air could change by so much that we would end up killing the patient. And I had not realized that air pressure changes by that much. So we needed a differential pressure measurement so we could know what background pressure was. So I soldered in a second BMP280, and I added code to check the ambient pressure on every single breath. So now we were not only measuring the patient pressure, we were measuring the air pressure, subtracting the two to get the real pressure. Now this ventilator could be used in a moving elevator, it could be used in a helicopter, it could be used in an airplane. Okay, so now I've got a video. I sure hope this works.
This is a demonstration video to show the parts of the University of Florida ventilator. Right here we just have stock standard pressure regulators. You can get them from Home Depot, and they drive a pressure that goes over to a lawn sprinkler. The lawn sprinkler is part of the inspiratory system. In that T there are two components that are simply mechanical. One is an overpressure valve, the black part on the left, and the other is an anti-asphyxia valve, the white part on the right. And if a negative pressure shows up in the system, that will open and allow the patient to breathe. From there, the inspiratory system pushes air towards the patient through that tube and over to our fake patient. You can't tell it, but inside there's a small orifice that basically reduces the pressure to protect the patient. Air goes into the patient. We have some examples of resistors. This is hard to do. And these resistors have certain amount of airway resistance, and the FDA tests require that we test various ones of them. The screen on the front of the ventilator, we're just using 1/2, shows the pressure on an analog dial that does not follow at all the fast transients that we actually see. That yellow fuel tubing is a airway pressure tap that goes into a Bosch BMP 280. And the air comes back from the patient into this part of the system. There's an expiratory valve here, but instead of being electrically controlled, that one's air pressure controlled, and we control it electrically through this solenoid gauge using some of the driving pressure to control whether or not that valve's open or not. To save space, we had to go around a U, and then we use this filter to smooth out the flow again. And then this part right here is fascinating. This is a homemade Venturi. It has an obstruction in it, and we measure the pressure up and down from that obstruction, and then it's just Ohm's law. By knowing the pressure drop and knowing the resistance to that obstruction, we're able to calculate instant by instant the actual gas flow in liters per minute, and it's astonishingly accurate. I could not believe we did that. Those two little cylinders are actually pneumatic low-pass filters. They're just a plenum. And then the signal from those goes into a differential pressure measurement system on the inside. This is one of my prototypes. We had to meet a whole bunch of FDA requirements. One of them is we can't have exposed conductors, so we used a CB microphone jack. The outside is not connected to anything. We power the system with a medical grade power supply. I don't know if I can do this, if I'm coordinated enough to do this, but this is one of my prototypes, and it's pretty ghastly how it's wired. You don't want to look at that too close. Over here, I have some examples of how all this is done. This is the expiratory valve, and it's simply a orbit valve that we have moved the spring from the top to the bottom and turned it from, I think it's normally closed, and we turned it into normally open. And then we pressure control it by running air into the top. The top circuit board here is actually a circuit board that was designed in India by Ashhar Farhan, who incidentally runs a company that puts satellites into orbit. A pioneering company in India, and it was built in Colorado, and we have quite a few more of these boards. You can see multiple different Arduinos. They come sometimes with the pins already soldered on, or else you can solder the pins yourself. It's not very hard. And we have a 2-line display. We use both 2-line and 4-line displays. They use the same connections. It's not a problem. They work off 5 volts. And that's basically the hardware of the ventilator, and it's basically driven by an Arduino with just a bit of circuitry around it to give us the signals. The benefit the Arduino gives us is it's got analog to digital converters, and it's also got digital outputs, and it's got a slew of both. So we don't have to add anything to it. It's got its own RAM, it's got its own ROM, and you can build just an enormous amount of stuff with just one chip. All right, so that's the end of the hardware demo.
Okay, so now I'm going to try to show the ventilator in operation. I need to stop. And is this going okay? Are people able to see and hear what's going on?
Yes, Gordon, it's running fine.
Okay, here we go.
Okay, so this is going to be a demo of this ventilator system, which I actually haven't been using for several days, so it's in a little bit of a disrepair. In a previous video, I hope I showed you the pressure inlet system, the inspiratory side that directs air to the patient. The air goes to the patient. This is a mechanical ventilator. And I want you to see right here, there's a dial that lets us see the pressure. 0 on the dial is right here. And right now it's coming down to 10. It's holding a pressure of 10 all the time. And that's to keep a patient's lungs expanded who's got boggy lungs from edema. This is the expiratory side, and this is the flow measurement system. And this is the controller, which is, as you see, homemade. If we want to give the patient more air, we just turn up the pressure on the dial and they'll get more air. The menu system for this was built by Ashhar Farhan, and I want Nancy to go ahead and let you see a little bit of this. Basically, it's constantly showing us the peak pressure that the patient received. These measurements are in centimeters of water. The volume, which right today is not measuring properly. The instantaneous pressure, so it's kind of like a dial gauge here. A series of alarms, and then on the bottom it's reading out in a ticker tape fashion every setting that we have made, and Ashhar hand coded a good bit of this. If I hit the menu button, then I immediately go into a menu system, and I can go down through menus to set pressure limits, end expiratory pressure, volume limits, what's called the I to E ratio. I can change how it ventilates, what duty cycle. I can reset alarms, and then there's a thing way down here to reset the I2C bus, because we were very concerned that we would have problems with the I2C bus. We never did, really, but we built it to be careful about that. So while I'm using this, I can, I'll probably set some alarms off because I'm going to change a lot of things. If I want to turn the ventilator off, I have to go through quite a few steps. I have to go off, and then I have to confirm, and then I have to do it again, and now the ventilator is finally off. There is no means to turn this off. It's got no power switch. Once it's powered, and normally there's a battery built in, it's impossible to turn it off. It's intended to be used and monitored by biomedical engineering. So we turn the ventilator on, and now the settings are here, and then I can set the breaths per minute, select, and then I can go up, 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 and unselect, go out of the menu, and now it'll be breathing 21 times a minute, a lot quicker. I can change the I to E ratio. If I go down.
Okay, you're at 3 minutes.
Okay, good. We'll stop soon. I'll change the I to E ratio. And now it's at 1 to 4, so now it gives very short breaths. Okay, so we'll stop this video and then we'll see if we can make another.
Okay, so huge legal issues in every part of building this thing. So we're trying to build it as carefully as we can.
Okay, so now I'm going to try to show you one of the more unusual features of what we had to do with this ventilator. Anytime you hit the menu button, you can cancel the audible alarms for 60 seconds. That allows you to think. This is a different kind of controller. This is a PID controller. Before we were using an adaptive controller. The PID controller tries to deal with the ringing of the system because the air bangs up against the closed valve. And the PID controller does a proportional integral derivative controller, and it actually manipulates this valve on and off very fast. You can see it. This is a LED attached to this solenoid, and it will very quickly hit the correct in pressure for the patient. It takes it only a breath, and it's there. When we go to the adaptive controller, things are not quite so spiffy. Gotta go down and go to the adaptive controller. Select, and then go out of here. And okay, now it's on an adaptive controller now, and it has to pick the exact one moment in time to close this valve again to keep pressure in the system. It opens everything to let the patient exhale, and it closes it before the patient can completely exhale, trying to keep a pressure. It's set to hit 10, but it's only hitting 5. And it is going to hunt with an algorithm to try to bring that number up, and it takes it a few breaths to get there. And it has some algorithm, so if it overshoots, it makes quick corrections, but it will gradually get us right to 10 centimeters and stop. And we were astonished at the accuracy that we developed. We were within 1 centimeter of water, which is not much pressure difference. It's already hit 10 centimeters. So that shows you the 2 control mechanisms that we used in the system, and we spent 2 weeks developing control systems, and we're not done yet. Okay?
So basically, we built a ventilator that could be used for surgery or for anesthesia, for ICU care in the third world. And it would offer most of the beginning portions of a real ICU ventilator, and it could be built for a few $100s, and it could be built in a garage in any third world nation in the world. We were busy trying to get this all over the world. We had an open source design, and we were getting responses from nations all over the world. of people who were trying to build this thing. The FDA had a very nice process for approving emergency use authorizations. They had got an industry group to build a white paper of requirements, and a document to explain the application process. We were supposed to have entered into an interactive process and then do a formal decision system with them. The problem I ran into was they referred to, this was written by an industry group, so they referred to all kinds of standards. We didn't have the standards, and they cost tons of money to get copies of these standards. Luckily, one of the UF engineers, we had a slew of people working on this team, meeting every morning at 9 o'clock, found copies that were available legally for their purpose. We had to answer like 100 different technical questions. We split the technical questions up into groups, and I took some of them and other people took some of them. And we would have to read the standard and tell them whether or not we complied with the standard or how close we came. This is a huge amount of paperwork. Okay, we were very new at this emergency use authorization. We were making boo-boos. We had no protection for the outside volunteers. So I forced the issue that I did not want myself or other people getting sued, and we stopped work until the University of Florida came up with a way to do the background checks that they required before they would extend liability protection to all of us. And this is very important. If you're building something to be used, you find a way to protect the people who designed the darn thing. They had enlisted a volunteer company to help them work with the application to the FDA. We spun our wheels much more than was necessary. In retrospect, we made a lot of mistakes in dealing with the FDA. Have a brief review of the FDA documents avoided us to avoid many heartaches. I had purchased an ISO spec compatible monitor power supply, so that took care of the power supply issues. I was aware of the waterproofing requirements, and so we worked on ways to do that. I used good standard ham radio design to avoid exposed voltages. Basically, in order to meet a lot of these standards, just do the best job you can. Think of how ICOM or Yaesu would build something and do it the same way. Several very simple ventilators were approved by the FDA. Jet Propulsion Lab, JPL, created a fantastic ventilator. It got approved, but it was horribly expensive. We built all this fantastic active control. The FDA did not want it. We had to strip it out. So the mistake was our fancy consultant and our engineering consultant team spent way too much time building stuff instead of spending more time to talk to the FDA to find out exactly what they wanted. A much simpler submission ended up, and it could have been done weeks and weeks earlier. And as a result, this thing, to my knowledge, was never approved because the need for it disappeared. It became obvious that we were not going to need that many ventilators. The ventilators that were shipped in New York were basically never used. And we should have had much closer coordination with the FDA. I wasn't in charge of that part, so I couldn't control it. But you needed to talk. What is it you really want, FDA? Do you want us to have this thing electronically controlled, or do you just want a simple mechanical valve? All of the source code that was developed is on Ventilator Developers at groups.io. The sea salt page at University of Florida has many specifications. You could easily manufacture one or more versions. And so this may well be used in third world nations that cannot get a ventilator. I was trying to get to Kenya on a medical missionary trip, and basically I was told that there, if someone had to be ventilated more than a few hours, they were just allowed to die because there were no ventilators. I'm going to just mention a few of the other things that our Alachua County group has done. We do HSEEP, Homeland Security Exercise Evaluation-based deployment exercises. We hold in normal years emergency comms conferences. We built a web server that could provide information to people who are in a shelter. We have helped with VHF-based Raspberry Pi WinLink servers. We write books. We try to create examples of how things can be done, providing ways for ham radio to get more and more in the professional realm of actually going to be called upon rather than ignored, as happened in Iowa. And that's why we're running this exercise on March 19th. We're actually going to have a resource net where people who don't have any clue what's going on will be able to join the resource net and get briefed on the exercise and be given a mission. And then they'll go to the command net, and the command net, they can execute their mission and be part of the real exercise. So if anybody wants to get involved with that, I'd really encourage you to look through at least some of the documentation, register with if you can, or at least show up on the resource net. And that basically is that. I have some other projects, but I'm not gonna show those right now. So now what do I do? Are there any questions?
All right, you can now unmute yourselves, and we have 5 minutes before we need to transition into the next program or start the transition. You can unmute and ask or put your questions in the chat.
Hey, Doc, Mike Lunsford here. Was this by any chance ever tested on a patient, and what was the result after that?
No, to my knowledge, it was never tested on a patient. I have no doubt it would have done fine. I took care of patients on ventilators for 30 years in the operating room, and this was a fine ventilator. I would have been very happy to use it.
It helps when you have someone on your team that was an anesthesiologist for how many years was it? 30 years? Hey, that's a big help. It's also a unique lifetime experience. I mean, you never get to work on that kind of project, but maybe once. And I'm glad you had that experience. You actually can be part of that.
We made good news for ham radio operators. We demonstrated that we really needed people with this broad level of skills if you're going to really build something. The mistakes we made were in administrative areas where we built stuff that was just not wanted by the FDA. And it's a legal environment in the United States. So the stuff we built may be very happy in Africa, but in order to get it approved in the United States, you got to do exactly what they want and nothing more.
All right. Does anyone else have any other questions? And if not, no one's in the chat. We'll go ahead and we'll end the stream on YouTube, and then give everybody a break. We'll leave it open for you to chat, and let Mike KB4FHP get ready for his presentation. So if there's no other questions, we'll end the stream on YouTube. And again, this is all new ground, and then we'll start it up about 1 minute before 10, but we'll leave the Zoom here on in between.
Thanks very much, guys. I've got to head out temporarily to a different meeting. I'll be back later on.
And don't forget, you may applaud by the reactions on your screen. It'll show the clapping of hands on there. So, but being we can't do it to applaud in person, so if all of us tried at once, only one person will come through.
Thanks, guys.
Gordon, thank you very much for the good presentation. We look forward to your presentation towards the end of the day on JS8. That's going to be quite interesting to.
That's going to be kind of interesting too. Yep. All right. See you guys later.
You always think outside the box a little bit, and you try, and you use your geek, your geek processes for the benefit of everybody. So we appreciate it, and thank you very much for the presentation.
All right. Thank you, guys.
All right. At this time, we're going to end the YouTube stream. We'll leave the Zoom on, and our section manager, I made him a co-host, so in case my internet connection disappears, I have my router on a UPS and my modem and my laptop's battery power. So if the power flickered, I wouldn't go off. But you never know with satellite internet, they might bump me off, so that way our Zoom don't turn off.